Okay, in this tutorial, we will be talking about the unit load method applied to statically indeterminate structures. So in the previous class, we did an example on determinate structures. Now we're going to study indeterminate structures. So what are indeterminate structures? Indeterminate structures are where the number of unknown reaction forces exceeds the number of equilibrium equations to solve the reaction forces. Okay, let me say that again. For indeterminate structures, the number of unknown reaction forces is greater than the number of equilibrium equations to solve those unknown reaction forces. Okay, so usually if you have two unknowns, you need two equations. If you okay, let me just start from the beginning. If you have one unknown, you need one equation. You have two unknowns, you need two equations. If you have three unknowns, you have three equations, right? But what are the equilibrium equations in static equilibrium problems? You're only limited to three. Okay, so what are the three? Okay, you have sum of all horizontal forces equals zero, sum of all vertical forces is equal to zero, and sum of moments about a given point is equal to zero. These are three equations that describe static equilibrium. There's nothing else. It's only these three. So horizontal forces in equilibrium, vertical forces in equilibrium, and moments about a given point is equilibrium. So that's it. So that means if I have four unknown reaction forces, I I can't I'm unable to solve for all four of them. Okay. So how do you deal with this kind of problem? Okay. How do you deal with statically indeterminate problems? Okay. So what we do is we will apply the unit load method. Okay. So this is where unit load method comes in handy. Okay. We're able to solve statically indeterminate structures. Okay. So what we've been learning up until this point, right, is statically determinate structures. So using force equilibrium, using moment equilibrium, we're able to solve for the forces. But in this case, the equilibrium equations are not enough. We simply have too many unknown reaction forces that the equilibrium equation isn't enough information to solve for all of them. Okay, so the trick is we will use the unit load method. Okay, just like we learned in last class. So this question alone is quite heavy. Okay, so bear with me. And I thought about it, how to explain it. So what I'm gonna do is I'm gonna present the solution first, then explain it. Okay, it's a bit too difficult to explain it first, then present the solution. Okay, it's difficult to explain why I do what I do, then show what I do. Okay, so I'm gonna present the solution first, then I'm gonna explain it. Okay, so different from how I usually handle my classes. Okay, so how can we tell that this is a statically indeterminate problem? Okay, let's first read the question. A steel spring ABC of uniform section is firmly placed on a firmly clamped at A and is restrained from moving horizontally by the guide at C. Okay, so the guide is referring to this slot here. Okay, so the spring carries a vertical load W, so there's a externally applied force here at C. Show that the deflection at C in the direction of the load W is equal to, okay, so 10.24 WR cubed over EI. Okay. Consider bending effects only. Note that the degree of indeterminacy is 1. Okay, so how do we know that? How do we know that this is a statically indeterminate problem? So we need to identify the reaction forces acting on the member. Okay, so that means we need to draw a free body diagram. Okay, free body diagram of this member. Okay, so when I say free body diagram, I mean you just take the member only without anything else. Okay, so who are the characters that you see in this figure? Okay, you see this wall. Okay, you see this member. Okay, member ABC, and you will see this slot. Okay, so these are the three things that you can see in this diagram. If I want to draw a free body diagram of this ABC alone, the member ABC alone, that means I must remove the wall. Okay, I must remove the wall and I must remove the slot. Okay, so let us go ahead and do that. So I'm gonna just do it beside here. Okay, so now as you can see, the slot is missing and the wall is missing. However, when I draw a free body diagram, wherever I cut it away from the other items, so I cut it away from the wall and I cut it away from the slot. Okay, when I say cut, I mean remove. So initially it was making a contact. Okay, it was making contact with the wall, right? So wherever it make a contact, there must be reaction forces. So what are the reaction forces at the wall? Okay, because this spring is built into this wall. Okay, there will be a reaction horizontal force, reaction vertical force, and a reaction moment. Okay, because built in, there will be three things. Okay, reaction moment, reaction vertical force, reaction horizontal force. Okay, then what about this slot? Okay, so this slot is free to move vertically, right? It's free to move vertically, means there are no reaction forces that will restrain the vertical movement. Okay, so there's no vertical reaction force. Okay, but you see, this slot, right? This slot is like this. So it restrains horizontal movement. If it restrains horizontal movement, that means there must be a horizontal reaction force. So there's some horizontal reaction force. Okay, so I'm going to draw it like that. And then I'm going to assume that C is free to rotate, right? This point C, I think is free to rotate within this slot. Okay, so it's free to, so it's actually able to rotate within the slot. So there's nothing restraining rotation. Okay, so that means there's no reaction moment. So there's only reaction horizontal force at the point C. Okay, so let's count the number of reaction forces we have. 1, 2, 3, 4. So there are four unknown reaction forces, right? Four unknown reaction forces. Then what about the number of equilibrium equations? Remember, we have 3 equilibrium equations. Okay, 1, 2, and 3. Okay, so 1, 2, and 3, whereas we have 4 unknown reaction forces. So to find the degree of indeterminacy, you take the number of reaction forces minus the number of equilibrium equations. So we have 4 minus 3 equals to 1. So that's how I get the degree of indeterminacy. You take the number of unknown reaction forces minus the number of equilibrium equations. Okay, so that's how I get the degree of indeterminacy. Okay, so how do we solve this problem? Okay, like I said, I'm just gonna lay out my steps first, then I will present, I will explain what I'm doing. Okay, so, okay, first things first is we need to draw a certain free body diagram. So what I'm gonna do is I'm gonna draw the free body diagram like this. So here's the spring, here's the wall. I will remove the slot. Okay, so you see, the wall is still here, the member is still here, but the slot is removed. So if I remove the slot, that means I must replace it with the reaction forces. So remember, it had a reaction force like this. Okay, according to the question here, we call the reaction force HC. Okay, you can call it anything, but for the sake of discussion, let's call it HC. Okay, so now what? Okay, so what I know is that C is restrained from horizontal movement, right? You see, we know it is able to do vertical displacement, right? Because I apply this force W, it's gonna displace vertically. But is it gonna displace horizontally? No. Why? Because it's fixed within the slot. So it cannot move left, it cannot move right. So it's not allowed to move horizontally. So I know after I apply this force, the vertical deflection is actually zero. The horizontal deflection is zero because of this slot being restraining it from horizontal movement. So I know it cannot move left or right. This means that I can claim delta Cx is equal to 0. Means the deflection of C in the x direction, okay, in the horizontal direction is 0. You agree? Because C is restrained to move along the slot, so it cannot move horizontally. Therefore, I know for a fact that the deflection of C in the x direction is 0. Okay, so let us write that down. And then remember that the formula for the unit load method is, okay, the deflection is equal to all the all the virtual complementary strain energy. Okay, all the virtual complementary strain energy. Because we're only asked to consider the bending effects only, so that means we need to do the integration. But how many separate segments are there? Okay, so let's check. So remember, the way to check separate segments is you must check the loading. Yeah, you must check changes in loading and changes in beam properties. Okay, so let's start from here, from C. Okay, as I scan through this, you must ask yourself whether there's changes in loading or changes in beam properties. So there's, there's no changes in loading or beam properties. And okay. So when I reach B here, then it starts to curve, right? Okay, so we will consider this other curve portion a separate segment. Okay, so we have two segments. One is BC and one is AB. Okay. 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 So let's go ahead and write that down. So we have two separate segments, right? Which is this. So this is the formula for virtual complementary strain energy for beams due to bending effects only. Okay, so pay attention because the segment AB is a circular arc, right? Circular arc. I'm not going to integrate it with respect to x. I'm going to integrate it with respect to the arc length. So instead of x, it'll be s. Okay, the arc length. Okay, because the segment BC is straight, I'm just gonna integrate it with respect to x. Okay, so it's a linear coordinate system. Okay. Okay, so what's the next job? The next thing I have to do is find these internal moments. Okay, find the internal moments. Okay. Okay, so the internal moments, what I have to do is I have to look at my diagram. Okay, I have to go back to my diagram here. Okay, so this is the center of this arc. Okay, so let's let this arc start here. Then we draw somewhere in the middle here. Okay, so what we do, we take a cut. Everything behind the cut, we throw this away. Okay, throw this away means we don't focus on it. Then wherever we make the cut, we replace it with the internal moment. Okay, the internal moment MAB. Right? Remember this is point A, B, and C. Okay, so I assumed I assumed clockwise as positive. So sum of M equals to 0 for the segment AB, where I'm taking clockwise as positive. So let's check. Okay, so now you pay attention to moments acting on the rest of the segment that we did not cut away. So who do we have? We have MAB and HC, right? MAB and HC. That's the only two loads acting on that member. So we have positive MAB. Then let's take a look at HC. So how does HC provide a moment about this point, about the cut? So remember, we are taking moments about the cut. Okay. So actually, you must see this carefully. Okay. So this is the radius. Okay, I'm going to draw a straight horizontal line through the cut. This. See, do you notice that this is the moment arm for HC? Okay, so remember, moment is equal to force times distance, right? This distance is the perpendicular distance of the force line of action from the pivot. Okay, right now this is the pivot. Okay, the cut is the pivot. The force is HC. Then this is the D, the distance. Okay, so how do we find this? Okay, so you have to use a bit of trigonometry. So we know that this arc subtends an angle of theta. Okay, so this is theta. Okay, then this over here, do you see this right angle triangle? This is a right angle triangle. Okay, this is the radius r. Okay, so if we have a right angle triangle, angle theta, this is r, and then we want to find this. Okay, we want to find this. Let's call it L. Okay, so this is L. So with respect to theta, this is adjacent, this is hypotenuse. So we need to use adjacent and hypotenuse is cosine. So cosine theta is equal to adjacent over hypotenuse. So L is equal to r cos theta. Okay, so I'm going to replace this on my diagram with r cos theta. Then what is this entire length? This is actually the radius of this circle, right? This is actually the radius of this circle. So this is actually r. So to find d, right? D is given by this radius minus r cosine theta. Okay, I hope you can see that. So actually, D is given by the radius minus r cosine theta. Okay, and that will be the moment arm of HC away from the pivot. Okay, okay. So why am I finding this? Because I want to find this distance here. Okay, okay. HC actually provides a moment about this pivot. So I'm taking force times distance. Okay, force times distance. Okay, so that will be the moment due to HC. Okay, so let's see it acts in the anti-clockwise direction. So it's actually negative. Okay, so it'll be negative HC r minus r cosine theta. Oh yeah, don't forget. I forgot. I forgot about including this W. Okay, actually you need to draw W in your free body diagram. So actually there's W here. Okay, so W also provides a moment about the pivot. So let's find the moment arm of W away from the pivot. So what is the distance between W and the pivot? So let's clean this up a bit. So W is along here, the pivot is here. So we want to find this distance, right? So we know for a fact that this is 2r. This is what is stated in the question. This is 2r. Okay, now we need to find this remaining piece. Let me just highlight it here. Okay, this part. So how do you find that part? That part is actually this part of the right angle triangle, right? So let's call this L2, okay? So with respect to the angle theta, right? L2 is opposite, right? This is opposite, this is hypotenuse. So I'm going to use sine. So sine theta is equal to opposite over hypotenuse. So L2 is equal to r sine theta, okay? Okay, so I know here to here is r sine theta, and then the remaining part is 2r. So to get the moment arm of W from the pivot, it will be 2r plus r sine theta. Okay? So, and also what's the direction of the moment? As you can see, with respect to the pivot, it will be a clockwise. Okay, so clockwise is positive in this convention. So it'll be positive W 2 2r plus r sine theta equals to 0. Okay, so we make MA be the subject because we will substitute this into our integral later. Okay, I also expanded the term. Okay, what else? We also need to find the internal moment at BC, right? So sum of moments in the member BC. Okay, so sum of moments in the member BC Okay, so how do we do this? Okay, what we need to do is, okay, we start from here, we start from this end, go to somewhere in the middle of BC, okay, take a cut, throw everything away. So I'm gonna throw all of this away, and I'm only gonna pay attention to everything before the cut. Okay, so what I'm gonna do is I'm gonna take moments about this cut. Oh, don't forget the internal moment, right? We must apply an internal moment here, M BC. Okay, so who is gonna cause moments about the cut? So first we have MBC, W, and HC, right? Okay, so these are the three loads which can potentially cause moments about the cut. So we have MBC. Who else? W, right? W will cause a clockwise moment. Yeah. So clockwise is positive. So W plus W times what's the distance? The distance is X. Okay. So this distance is X. Then what about HC? Okay. HC X through the pivot. So its distance from the pivot is 0. Okay. The moment arm is 0. So therefore it does not contribute any moment. Okay. So we make MBC the subject. Yeah. Okay. So now we have to find the virtual internal moments, meaning the small MAB and the small MBC. Okay, so now we have to do that. So what do? We need to do the virtual load analysis. Okay, the virtual load analysis means that, okay, we need to do the same thing. So we take the same free body diagram, except we must apply the unit load. Now, how am I going to apply this unit load? Right? The unit load that I'm going to apply is this. So remember, we are finding delta Cx, right? Delta Cx is the horizontal deflection at the point C. Okay, if I want to find the horizontal deflection at the point C, I must apply a horizontal unit load at point C. So I'm going to draw a horizontal unit load like this with 1 Newton of magnitude. Okay, it could be left, it could be right, it doesn't matter. Okay, so for the sake of discussion, let's go for left. Okay, and now what I'm gonna do is I'm just gonna do the same thing. Okay, so find the virtual internal load here. So go somewhere in the middle of AB, take a cut. Okay, go down. Okay, so this is my MAB. Then now let's take moments about the member AB. So the virtual moments for the member AB is equal to 0. So who is contributing? Who's gonna contribute um, some moment to the member AB? We have MAB itself and this 1 Newton load, right? So what's the moment arm of this 1 Newton load? Okay, it will be this distance. Okay, so I'm going to recap how to get this distance d. So it's given by this radius minus away this red part of the right angle triangle. Okay, then if this is theta, this is r, then the red part of that triangle is given by r cos theta, right? Because it's adjacent. Okay, r cos theta. So to get d, it'll be r minus r cos theta. Okay, so that's how I get the moment arm of the 1 Newton load. Okay, so first thing first, we have MAB. Then the 1 Newton load will be providing a anti-clockwise moment. Okay, so here clockwise is positive. So if it's anti-clockwise, it'll be negative. 1 Newton times the moment arm r minus r cosine theta equals to 0. MAB equals to, okay, r 1 minus cosine theta. Yeah, okay, so I factorize out r. Okay, now do the same thing for the moments about the second VC. Okay, so what am I going to do? Okay, what I'm gonna do is I'm gonna start from here. I'm gonna go somewhere in the middle of BC, take a cut, throw away everything else. Okay, draw the virtual internal moment MBC, and then see take moment equilibrium about MBC. Okay, so the only two loads acting on segment BC will be MBC and this 1 Newton load. Okay, so let us take a moment. So we have positive MBC. Then what about the contribution of moment due to 1 Newton? The 1 Newton load actually does not supply any moment, right? Because this is the pivot, right? And then its distance from the pivot is 0. The moment arm is 0, therefore it does not contribute any moment. Okay, so we don't need to include this in the moment equilibrium. Therefore, MBC is equal to 0. Okay, perfect. MBC is equal to 0. Do you know what that means? So if you come back here, okay, if we substitute this to be 0, right, then this whole integral will be gone. Okay, because you're integrating 0, the integration of 0 is just 0. Okay, so we only need to care about the first term here. Okay, we only need to care about the first term. So let's write this down again. So the horizontal deflection at C is given by, okay, so we need to substitute our results that we found here. Okay, so we need to substitute the value of MAB and small MAB that we got from earlier. Okay, now remember what is the value of delta Cx? The value of delta Cx is 0, right? Because the point C cannot move in the horizontal direction, right? It cannot move left and right because it's blocked by the slot. Okay, if it's blocked by the slot, then the horizontal deflection is 0. So we can substitute this to be 0, right? So 0 equals to, then we substitute all the other results. So MAB is what we got earlier, right? So it'll be this here. Okay, so we're gonna substitute this whole thing here. Okay, so HCR minus HCR cosine theta. Oh, I'm gonna move this over because it's not enough space. Okay, then we're gonna substitute MAB, right? MAB is given by R1 minus cosine theta. Okay, sorry, this is integrating with respect to ds, right? Over EI. Now, remember, whenever we are integrating with respect to the arc length, right, we will replace ds with r d theta, right? Because you remember from A maths, s is equal to r theta. So if the radius is constant, then any infinitesimal change with s will correlate with a infinitesimal change in theta. Okay, so change in s is given by the change in theta where r is constant. So ds is equal to r d theta. So you replace it with r d theta. Okay. Okay. So what are we gonna do? We're gonna do some simplifications here. Okay. So what I'm gonna do is I'm gonna remove all the constants. I'm gonna factorize out all the constants to the front of the integration. Okay. So you see, in the first bracket here, in this long bracket, okay, what can you see common factors? Okay, what common factors can you see? You can see R, right? R is a common factor. See R, 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 R. Okay, so there's a common factor of R here. Okay, so we know there's a common factor of R here. So there's an R somewhere inside here. Then what else? You can see another R here, and then you can see another R here, right? So we have three R's multiplying together. I'm gonna factorize them out. So R times R times R will be R cubed. Okay. EI is also a constant, so I can take that out. So divided by EI, that's a constant. Then you just leave back the remaining terms. So all the R's in this long bracket is gone. So what we're left with is HC minus HC cosine theta minus 2W minus W sine theta. Okay. Then this second R is gone, so we're left with we're just left with the 1 minus cosine theta, 1 minus cosine theta, and then this R is also gone, so with respect to theta. Okay, okay. So because this side here is 0, right? If I move these constants, if I move them to the other side, it will just cancel with that 0, okay? So what I mean is, if I divide both sides by the same thing, so this I divide by r cubed over ei, then this divided by r cubed over ei, okay? This and this will cancel. 0 divided by anything is just 0, okay? So that means I can effectively just remove this constant, okay? In the front, I can just remove this term. What am I left with? Okay, so what I need to do here, right, is brutally take this and expand it with this, okay? I'm going to multiply every term out, okay? So if I do that, multiply this with this, okay? And so on. Yeah, I'm going to expand this whole bracket out. So bear with me, bear with me. A lot of maths going on. So HC minus HC cos theta minus HC cos theta plus HC cos square theta minus 2w, okay, plus 2w cosine theta minus w sine theta plus w sine theta cos theta d theta. Okay, so we forgot to substitute the limits of the integral, okay? So let's go ahead and check what's the limits of the integral. So you see, we are integrating from here all the way to here. So how many degrees did I subtend? Okay, how many degrees? So we start from here, right? Which is 0 degrees. Then we make a half turn, okay? A half turn, this will be 180 degrees. So what's 180 degrees in radians? 180 degrees is actually pi, right? Pi radians. So the limits of our integral will be 0 to pi, okay? So this will be 0 to pi, okay? 0 to pi radians. Okay, how am I gonna further simplify this? What I'm gonna do is, I'm gonna factorize, okay? So I'm gonna factorize all the HC terms. So you see, HC, yeah? So I'm gonna factorize this, HC, 1 minus 2 cosine theta, right? This cosine theta minus this cosine theta is minus 2 cosine theta, plus cosine squared theta, okay? And I'm gonna factorize all the w terms. So w, right? So plus w minus 2 plus 2 cos theta minus sine theta plus sine theta cos theta d theta. Okay, excellent. Okay, why is this excellent? Because now in this form, right, you can easily do this in your calculator. Okay, I generally discourage you from doing this by hand. Okay, it's definitely not easy. So what you can do is, okay, you can integrate this in your calculator. So you integrate 1 minus 2 cos theta plus cos square theta with respect to theta, and then you sub in the limits 0 to pi. Okay, so if you punch this in your calculator, right, this 1 minus 2 cos theta plus cos square theta, you integrate that with the limits subbed in, you'll get 4.71239. Okay, and then this HC, I just copy it down. Likewise for W. So what you do is you integrate this bracket. You put this bracket in your calculator, you integrate it with the limits 0 to pi. Okay, put this in your calculator. What you'll get is negative 8.28319. Okay, and this W, you just copy it down like that. Okay, so what's the meaning of all this? Okay, what this helps you do is find HC. So you make HC the sublet, you will get 1.75775 W. Okay, why? Because HC, right, is actually an unknown. Okay, HC is an unknown, right? Where do we get HC from? HC is something we get after we draw the free body diagram, right? We remove the slot, and then the slot is replaced by the reaction force, HC. Okay, the reaction force is unknown, so we need to find it in terms of W. Okay, we consider W to be unknown because it's an external load. usually we know how big an external load is. Okay, we control the external load, so therefore we take W to be an unknown, whereas reaction forces are, sorry, W is a known. Okay, we control external loads, therefore W is known, whereas HC, the reaction force, is unknown. Okay, so this this whole kerfuffle here will help us find HC in terms of W. Okay, so now that we found HC in terms of W, we can finally go ahead and find the vertical deflection. Okay, we can finally go ahead and find the vertical deflection of C. Okay, so to find the vertical deflection of C, okay, so delta C, okay, delta Cy, this is the unit load equation. So the unit load equation says that the deflection at a point is given by the sum of virtual complementary strain energies. So the virtual complementary strain energies are given by this, remember, MAB. Okay, so this uh yeah, this is the same as earlier. Okay, big MAB is the same as earlier. Now what about small MAB? Small MAB is not the same. Okay, small MAB is not the same because the virtual load, the unit load that we're gonna apply is different. Okay, so bear with me first. Yeah, and then MBC is also the same. Okay, so the big M's are the same because those are from the real force analysis. We've already done the real force analysis in the previous part. Okay, when we're trying to find delta Cx, we already did the real force analysis and we've already obtained MAB and MBC, so you can reuse that. But small MAB and small MBC are different because now the virtual load analysis will be different. So let's take a look at the virtual load analysis. So you draw the free body diagram. Okay, this is the wall. We already removed the slot, right? Okay, so to draw the virtual load analysis, you remove every external load, and what you apply is the unit load that you want. So you see, we want to find the vertical deflection at point C, right? So in order to find the vertical deflection, I need to apply a vertical unit load. Okay, so the vertical unit load, I'm gonna apply it like this. So a downward vertical load of magnitude 1 Newton. Okay, so based on this, I'm gonna find the virtual internal moments. Okay, so we start with MAB first. So you start from this point, go to somewhere in the middle of this point. Okay, take a cut, throw everything behind this cut, draw the virtual internal moment. So this is MAB. Okay. Now ask yourself, what are some loads that will act? What are the loads that will act? That will provide a moment about this pivot, about the cut. So it'll be this MAB and this 1 Newton load, right? So we take moments equals 0 about the segment AB. Okay, so this way is positive. So MAB is in the positive direction, so positive MAB. Then what else? So the 1 Newton load, the moment arm is from here all the way until the 1 Newton load. Okay, so that's the moment arm. Okay, so how do we find that? So it'll be this distance plus this distance. Okay, so this distance is r sine theta. Okay, just do the trigonometry yourself. It's what we did earlier, and this is 2r. Okay, so the moment arm is 2r plus r sine theta. Okay, then the direction is positive because it follows this positive direction. Okay, this is clockwise positive. So this is positive 1 Newton times 2r plus r sine theta equals to 0. So you make MAB the subject, it will be negative 2r minus r sine theta. Okay, now you do the same thing. You find the virtual internal moment at BC. Okay, so how do we do that? Okay, we start from this end. We go somewhere in the middle of BC, take a cut, throw everything away behind the cut. Then after that, draw the virtual internal moment. So this is MBC. Then you ask yourself, what can contribute moments about this cut? Okay, so what can contribute moments? It will be this MBC and this 1 Newton load. Okay, so remember, this is our coordinate, so this x. Okay, so we have positive MBC. So let's say we take moments equals to 0 about the segment BC. So we have MBC. Okay, the 1 Newton provides a clockwise moment, which here is positive, right? So here it will be clockwise positive. So positive 1 Newton times that distance will be x, right? So see, this moment arm is just x. Okay. So this is 1 times x. And BC is negative x. Okay. So now we're gonna substitute everything into our this expression, right? Okay. So we're gonna substitute this, this, and this. Okay. I'm also gonna pull out the factors that I can see. So this and this, I'm gonna pull out of the integration. So our delta Cy will be equal to, okay, pull this out of the integration. So I'm gonna substitute this in. So bear with me, it's a very long expression. Okay, then followed by the virtual internal moment. Okay, and remember, I'm gonna replace ds with r d theta. So r d theta. Okay, next the second integration. So the second integration, also I'm gonna pull out the EI. Okay, then what do we have? Okay, so MBC is given by negative WX. Then small MBC will be given by negative X. Okay, and don't forget the limits of integration. So remember, the circular arc here runs from 0 to pi radians. Then this straight segment here runs from x equals to 0 to x equals to 2r, right? The entire length of this straight segment is 2r as given by the question. Okay, so here will be 0 to pi radians. This will be 0 to 2r. Okay, so how am I going to simplify this? Okay, it's a bit hectic, so bear with me. So let's take a look at the first integration. So the first integration is this one. So what I'm going to do is, I'm going to factorize wherever possible. So the things that I can factorize are the r, right? You take a look at the first long bracket. You can always see r, right? R, 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 R. So there's a factor of r in here. Then in this second bracket, I can also see a factor of r, R, R. So I'm going to factorize out this r. Then don't forget here, there's a tiny, tiny r here, okay? So I have three factors of r. R times r times r will give me r cubed, okay? So I'm going to take those out. Okay, so I have r cubed multiplied by this constant, so EI. Okay, then okay, everything left behind will be just everything without the r's. Okay, so now I'm going to deal with this integral. Actually, this integral is easy, right? So negative and negative can cancel. And if I multiply this together, I'll get wx squared. So the integration of wx squared is very easy, right? It's very easy. So let's evaluate that. So integrate wx squared. So I'm going to copy down the w. Okay, copy down w. Then integration of x squared is power plus 1 divided by the new power. Okay, then our limits are 0 to 2r. Okay, then what else? Okay, what I'm going to do next is I have to expand these two brackets. Okay, so multiply them together. Okay, okay, and then if I substitute the limits of this integral, right? If I substitute 2rn and I substitute 0n, you will evaluate this integral, the second integral, to be 8wr cubed over ei. Okay, so how do we handle the first integral? Okay, so what I'm going to do, right? I'm going to factorize the common terms. So you see, these terms all have a common factor of hc. So hc, 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 hc. Whereas the second set of terms all have a common factor of w. W, 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 w. So you factorize those common factors out. Okay, so what I mean is, okay, and then the w terms, okay, don't forget your second integral result. Okay, so how do you do this? Okay, now after this factorized form, it's very easy to evaluate in your calculator. So what you press in your calculator, right, is integration from 0 to pi radians, this first bracket. Okay, so when you do that, okay, when you do that, what you get is, okay, don't forget your r cubed over ei here. Okay, so your r cubed over ei. Okay, and don't forget you can copy down this constant, this hc. hc. So I'm going to say it again. What you do is you press in your calculator, you integrate from 0 to pi of this ginormous expression. Okay, what you get is negative 8.28319. Okay, then what about the w term? Okay, so copy down w because w is a constant, so you may take that out. Then what you do is you punch the integration of 4 plus 2 sine theta, blah, 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 all this second bracket. Okay, you integrate it from 0 to pi. Okay, then you'll get 22.1372. Okay, and plus, don't forget this 8w. So 8wr cubed over ei. Okay, so what can you do? Do you remember where I saw this? Hc, right? We got it from earlier. See, we found Hc to be this. Okay, we found Hc to be 1.75w. So I'm going to sub this result in here. Okay, so this I'm going to replace it with 1.75775w. Okay, so you see, you can now evaluate this result. So you take this times this negative 8.28 w, right? Then plus this, you add this all together because now they're all in terms of w. Okay, so you can do this, and then you will get, okay, 7.5774, okay, wr cubed ei, okay, plus 8WR cubed over EI. Okay, so 7.57743 plus 8 is equal to 10.24. And then the common factor of WR cubed over EI, you copy it down. Okay, so let me say which goes to where. Okay, I know it's a bit confusing. But this, okay? So when I simplify this, it will become this plus the W. Okay? Then this is just this. Okay? Okay, so the whole thing in this bracket will become 7.57743 W. Then I multiply it with this. This is just this. Okay? This R cubed over EI was from the front. Okay? And then if I add the two terms together, so 7.577 plus 8 will give me 10.24. Voila! This is your result. Okay? And like I promise you, I will explain what I'm doing. Okay? So we know that this is a statically indeterminate problem. Statically indeterminate means we cannot solve for the unknown reaction forces. And this is a trouble for us. Why? Because earlier, when we wanted to find MAB, right, we need to involve the unknown reaction force. Do you remember? See, when we found the expression for MAB, we have the unknown reaction force. See, HC is the unknown reaction force. Okay, and we don't know what is the value of the unknown reaction force. So we need to solve for it. But this is a statically indeterminate problem. So you cannot use equilibrium equations to solve for HC. Okay, so how do we find HC? We must resort to using the unit load method. So how do I use the unit load method to help me find HC? Okay, I must know, based on the diagram, that the point C is restrained from moving horizontally, right? So there is no horizontal deflection. This means that delta Cx is equal to 0. Using this fact, I will apply the unit load in the horizontal direction for C. Okay, so that's why I wrote this. Okay, so delta Cx is equal to the sum of virtual complementary works. Okay, so I do the same process like normal to find the internal moments. So MAB, small MAB, MBC, and small MBC. Okay, then I will substitute all this into the integral, right? After I found all the internal moments, I go back to the deflection expression. Then I put it here. Okay, so I sub everything in. And then I know, remember, that the point C is restrained from moving horizontally. That's why I replace this with 0. Okay, I replace it with 0. And then for some reason, when you do this whole equation, right? When you simplify this whole equation, you simplify, you will find that you will get an equation. See, you'll find that you'll get this equation. Okay, this equation is one equation. Okay, so this is one equation, and there's one unknown, and the unknown is Hc. Okay, Hc is unknown because reaction forces are unknown. External loads, which is W, is known. Okay, external loads is known. So you see, that's the magic of the unit load method. It can help you solve for the reaction forces in statically indeterminate problem. Okay, how? You must choose a point where you know that there's no deflection in some direction. Okay, it could be restrained from the horizontal movement, or it could be restrained from vertical movement. If you know it is restrained, that means the deflection in that direction, okay, let's say it's restrained horizontally, the deflection in the horizontal direction is 0. So you apply the unit load method for the horizontal displacement, right? So you see, the for this horizontal deflection, right? In the virtual load analysis, I apply a horizontal unit load because I want to find the horizontal deflection. But I already know that the deflection based on the geometry is 0 because it's fixed within the slot. It cannot move left and right. So by using this magic, actually by using this fact, I can find single equation to help me find HC. Then I find HC in terms of W. Once I found HC, then I can find the vertical deflection. So you just do like normal in the previous class. So in the previous class, we already introduced you the unit load equation, right? So do this unit load equation, then you find the internal loads. So sorry, you find the internal moments, Then you do this complicated integration, right? Then you see HC popping up again. So that HC, right, you replace it with the result you got from earlier, right? The result when you were doing the delta CX, right? Delta CX helps you find the value of HC. It helps you find the value of HC. So this value, you substitute it into here, right? Then after that, voila, HC is no longer an unknown. You found it in terms of W. W is unknown. Then after that, you do the magic. You just do it as usual. You replace HC with the thing you found from earlier, the value you found from earlier. Then you are able to find the vertical deflection. Okay? I know this is a bit complicated, but what I recommend you to do is, okay, you listen to my video first. Then what you do is you try to redo this question without my help. Okay? So you do it all over again. Okay? And if you still can't do it again. Watch how I do it, and then put away the video, try it out yourself. Okay? Slowly you get the idea. Okay? Slowly the idea is, okay, you find a point which has zero movement in some direction. You take delta in that direction is zero. You do the virtual load analysis, but then you remember to equate it to zero. Find the unknown reaction force. Then you do the same thing for the vertical deflection. Okay? Don't worry, just watch and rewatch, learn and relearn. Okay? You trust me, you'll get there. Okay? It's a bit difficult because the algebra and the trigonometry of this question is really distracting. Okay? It's a whole piece of work on its own. Okay? But trust me, keep redoing it. I'm sure you'll be able to do it. Okay? Surely you'll be able to do it. Okay? So if you found this hectic video to be helpful, please donate to this channel. Thank you very much. See ya.